Okay, so kicking off Unit 2, our Unit 2, and therefore our Exam 2 when we get that far, are going to consist of two primary topics. The first of these is going to be kinetics, and then second we're going to get to equilibrium constants. So kinetics first, and as is often the case in general chemistry, there's always a catch-22 about which do we do first. The best way to talk about kinetics really is by using equilibrium, but then the best way to talk about equilibrium is by using kinetics. So we had to pick one, so we're going to go with kinetics first. So in Gen Chem 1, we would balance reactions. We would look at basically a starting state and an end state. We might do some limiting reactant calculations, some yield calculations and stuff, but never did we really talk about the time that it takes for a reaction to occur. And so now with this kinetics unit, we're going to start to approach the idea of, okay, that reaction that we're going to say happens. Now we're going to talk about, well, how fast does such a reaction happen? And so what we're going to do is we're going to end up, a lot of times we're going to be talking about this concentration, and this you'll see this over and over again, this brackets here, concentration versus time graph. And there are going to be some other graphs. We're going to do a lot of graphing and a lot of linearization in this unit. And so we're going to talk about a concentration versus time space here, where we might say, well, we know how much, like say we start out with a lot of reactant. We might be able to watch that reactant as it decays through the process of a reaction over time. And so the concentration is going down over time. That's what we're going to be talking about tracking when we're talking about the change in concentration over time. As an example, in Gen Chem 1, we might have used an equation like this, like for balancing practice or something like that. You've got hydrogen peroxide, H2O2 here, and this is going to be with a product of, in this case, H2O and O2. So the way we have written this here, right, it just says that hydrogen peroxide will decompose into water and oxygen. It doesn't say anything about how fast, right? So now we're going to delve into, well, like, is this instantaneous? Does this, if you have a mole, 1 molar concentration of H2O2, do we get zero molar H2O2 after a minute, after an hour, after a day? How fast does that reaction go? Do we ever get to zero concentration? Well, actually, do we ever get to zero concentration is kind of the next unit that we'll get to with equilibrium. For right now, we're just going to talk about how fast a reaction proceeds, not where it stabilizes out. That'll be next. Okay, and a big note here, a big note that for the way we teach chemistry here at Dalton State, calculus is not a prerequisite for this course. So, in doing that, I'm going to have to kind of dance around some concepts, because really our treatment of rate laws should use integral calculus, should use derivatives to talk about these slopes, and then integrals to integrate a rate law later. But we're gonna dance around that. So a lot of times I'm gonna use the term delta, where I would prefer to be using the derivative of concentration with respect to time, or really even better, partial derivative of concentration with respect to time, because there might also be a temperature axis, a pressure axis, lots of other axes that could be involved here. So know that I'm approximating things a lot of times by saying delta. If you do have the maths in order to treat this as a true derivative, then actually some things become easier. I guess not easier enough to teach you all of the process of derivative calculus in order to do it, but easier in the sense that it might be might be easy to see what I'm talking about if you just think of it as derivatives and integrals. I am sure that I have not thought of all the terminologies that I'm going to use, but I wanted to point out a few that I did think of. Starting with this this bracket here, right? So what I'm doing, I'm showing a square bracket with something in it. It might be A or B or something like that if I'm trying to be general about something, or I might put a component of our reaction, like for the hydrogen peroxide example earlier, I might say, change this to a pen here, and I might say concentration H2O2, right? So those brackets here, I'm going to specify, at least for this course, my square brackets are going to mean concentration. And then similarly, I might use subscripts to say, like, okay, that might mean concentration at time 0, and this then would be the concentration at some time t. And of course, that implies then that we're going to look at this as concentration as a function of time, and that kind of goes to that plot I started the presentation with, that we would plot concentration as a dependent variable on the independent time axis. And I also wanted to review a bit of concept from chapter 5. So please do look back at chapter 5, particularly the enthalpy section. Okay, so I need to assume that you've got enthalpy, and I think it might be a really good idea to go back and review that section particularly. I want to make sure that you understand the idea of a state variable. So here, this is figure 5.24 from your text, and so what we're looking at here is a change in energy between two states, right? We have a state variable, but what I mean by state variable is it doesn't matter the path that we get there. So consider topography around Dalton State. So let's say that I leave chemistry building here at Dalton State, and I go directly behind us and up the hill, walk all the way to the top of the ridge, and along the top of the ridge to the Doug Gap Battle Park. Okay, so you see where I started at the school, and then where I ended up at that park up at the peak of the ridge going over there. And I want you to think about the change in elevation that I've experienced there. Okay? Now, consider a different scenario. Instead I leave Peoples and I ride with somebody else to, let's say, to the trade center. And then at the trade center, change cars, and then I drive a different vehicle up to the parking lot there below Doug Gap Battle Park, and then get out, and then I walk into the park there, right? Okay, so think about the change in elevation that I experienced in that case. And the idea of a state variable is that change in elevation is exactly the same if I ended up in the same spot, regardless of the path that I took to get there. Okay, so hold that analogy in head there while I think here about, okay, look, we have starting out, we have carbon in its reference state here, just solid carbon, and we have oxygen gas also its reference state here, and we can look at the energy difference if you take that carbon and the oxygen and you combine it to make CO2 gas. All right, so we have a delta H, a change in enthalpy, negative 393.5 kilojoules per mole. So, okay, but if instead, if we had combined this solid carbon and this oxygen gas to generate carbon monoxide and still some O2 left over, and then we went ahead and took those intermediate products and we combined them to make final product of CO2, we might have, for these steps in between, we might have a delta H for this step and a delta H for this step, but it turns out that our overall change in enthalpy between the starting and the end state, are independent of how I got there. And that can be important for trying to figure out some of the kinetics and later some of the thermodynamics when we get there. And these are called state variables when this happens. Okay, and so to illustrate this same process here, now I want to point out before I start that now I'm talking about a different plotting space here. This time on my y-axis I have total energy of the system, or maybe we should think in terms specifically of enthalpy for now. We're gonna staple another concept to enthalpy later, but let's just talk about some form of internal energy. Enthalpy would be fine. And then on the bottom here we have I've plotted it as reaction progress. Now for now we can think of this as time. I would like for it to always be time, but later on it's going to get more complicated depending on what all we have to do to get a reaction to proceed. I think a simplification we can think of this as time. But so the point of it is, just like on the last slide, we could have our starting reactants up here, and we could watch the change in their enthalpy. Okay, so we've got an initial enthalpy state, and then it's going to drop down to a final enthalpy state. And so we can talk about a delta H between those two states. But it really doesn't matter if it all drops in one big concerted action here, or if it were to drop to an intermediate state, but then that intermediate state further reacts, just like our carbon monoxide did, to make a final state in the same place. Well, it doesn't matter. The orange curve and the composite of these two blue curves, they end up with the same overall delta H because they're a state variable. And then some more terminology. And this diagram may not be from your textbook. I believe this one comes from what is likely to be your next course in your sequence, organic chemistry. But what I wanted to do is I wanted to use it to point something out here, because we do talk about some in some of our theory part of this. We're going to talk about transition states. And I wanted to be explicit because I'm afraid we don't enough be explicit with what we're talking about. So here I've got reaction progress on the bottom, and it's okay if you think about this as time for right now. Really, we don't care if it's a even scale in time. What we care about is just kind of a graphical representation of where we started versus where we ended. And so this system shows that we have a delta H here, that our products have a lower delta H value than our reactants. So products minus reactants is going to be a negative delta H, which implies an exothermic reaction, right? Well, so an exothermic reaction is going to release energy, and later we'll learn that that's not guaranteed to be thermodynamically favored, but it probably will be. So let's say for now that this is a thermodynamically favored process, and that we're only talking about delta H over here, and not the new thing that's going to come up in Unit 4. So if that were the case, right? Well, that is thermodynamically favored. Then you would think that anytime you had A and B lying around, that they would automatically go straight to C and D. But it isn't the case, because often there is this. Here we've got it labeled as E sub A. You have this we call a transition state with this double dagger, AB double dagger here, where basically these reactants have kind of gotten together here for a moment. Usually it is for a very, very short period of time. You have this elevated energy, right? So kind of going uphill. So think of it like a car. So you want your car to get from here to here. Well, there's a good situation where gravity is going to help you, right? Because this is higher than this endpoint down here. But the problem is you've got to get it over the lip. You've got to get it over the edge of the hill first. So you got to push your car kind of up to the transition state, and then gravity will do the rest. Well, the chemical reactions are often that way as well, right? So, but you may have to get over the hump, and the hump might be called this activation energy that we need to get things started. I wanted to put out a math thing or two here. I just grabbed this site I found that talks nicely about some algebra here. I like to promote some of these math sites sometimes that help me to teach students, and so kind of giving back to promote them a little bit. I don't know anything about these folks, but I liked their discussion of polynomial degree. We're going to talk about polynomial degrees a little bit, but we're going to talk about the degree of a reaction. So just think that through and review what it means. I am afraid that our usage in chemistry will be slightly different than it is in pure maths, so be flexible when we get to that, and we'll talk about what degree of a reaction means as far as kinetics goes. And also I would like for you to review, so I'm not sure where you might have seen this before, but I suspect in something like 9th grade algebra, but I do want you to look back at your function orders here. And so you've got here, we've got what's called well, it's a zero order derivative. The concentration versus time is a first order curve, and therefore the derivative, or the delta would be one order lower. So since this is a linear, y equals mx plus b, the x is raised to the first power, right? Well, so your derivative is going to be one order lower, so a zero order rate of change, kind of like your slope. Or you could have so you probably see that as a quadratic, right? And so second order concentration versus time, and your change. So if we talk about the kinetics, it'll be first order kinetics. Again, that's a second order curve, and so the rate of change will be one less than that, or first order. And a third order, this could be like a cubic function here, and you can have a second order rate law, or second order kinetics. Now we're not, I don't mean to imply that these are the only options. So please don't, especially my chemistry majors, please don't lock yourself into thinking, well, it's got to be zero, first, or second. No, your options are near infinite here. But to keep things simple, we're going to try to, for the most part, try to look at things and pigeonhole them into, oh, that's a zero order thing, or oh no, that's a first order or a second order. And we'll try to avoid some of the more esoteric rates that are out there. So some more concepts that we'll have with this, and please do read your text. And also, I've linked another text here. This one's also free. Chem Libre is another nice free site for textbooks. And, it does an even better discussion than your textbook of some of this rate calculation stuff. And so you've got some other things to consider, right? So we'll talk about half-life and how half-life is calculated. I hope that you saw that in the nuclear section in Gen Chem 1. But the interesting thing with the nuclear section, where we really introduced half-life for the first time, is that we're only considering one of the possibilities where everything is a first order rate constant, and so when you do that, you have you're only looking at one of them. Now we're going to talk about some other ways that we can get half-lives for our systems, for our chemical systems, our reactions. And I would note that a good trick with this is that these different units tend to have, these different rate orders tend to have different units to go with them. And we'll talk about how those work. Okay, so what is this about? So thermodynamics, that's going to be in Unit 4 later on, is whether or not a reaction is likely to take place. Fine, we'll get to that then, but for now, let's say assuming the reaction does take place, how fast is it? And so that's what we're going to be on about here, is how fast does a reaction proceed. So our reaction rate is, we're going to define it here as the change in concentration of something participating in the reaction. So that could be reactant or product. The change in concentration over time. Okay, so now generally we're gonna measure our concentration in molar units. So we might say our molar concentration per unit time, like per second. So molar per second would be a reaction rate. Okay, so a few things to look at with that. We'll talk about the rate of change of the reactant side. In this case, I have it as A. So we could talk about the A, or we could talk about the rate of change of the product side. But think about what they're doing, right? So what's happening to your, well, let's look at B first. So for a given reaction, A goes to B, what's happening to your concentration of B over time? It is increasing because you're making B from A, and similarly your concentration of A should be going down over time. So if you plot these, right, then the rate of change, if we talk about rate of change or just straight delta, and I'm going to make the analogy to distance in physics, right? So we're going to talk about distance as a scalar quantity here, right? So the rate of change is just going to be a delta, right? So just kind of make the positive and negative work depending on whether you're talking about reactants or products. So if you're talking about reactants, well, your overall rate is going to go negative, right? It's going to go down. And if you're talking about products, make it make sense. You know how fast it's changing. Don't tell me that you have a negative rate of change for B because it's a product. So if its rate is going down over time, something else is going on. We don't have a simple system where A is becoming B and that's all that's going on, right? So if it decreases with time, then delta A is negative. So I wanted to plot them just to look at how this looks over time, right? So if you start with a system that is all one thing and you just time it, right? See, what's happening here is over time the black dots are turning into red dots more and more, right? So that's a change in the system overall. I like this diagram because it actually, if you actually bother to sit down and count and plot these on a graph, it does make a nice clean curve the way they did it. So that's kind of cool. And that's the plot that it would make. So what's happening is, right, so if we look at, so A, and it's color-coded black here, versus B, our product, which is color-coded red, right? So here's a graph of A versus B, and as A is dropping, concentration over time, B is increasing its concentration over time, okay? So I hope that makes sense as is, right? That you have this rate of A and B, and then we're going to sneak up on the idea of there is an overall reaction rate. I'm going to talk about it in terms of the reaction arrow. It's a simplification, it's a simplification that I've found really useful for students going further, is to talk about how many reaction arrows, or how many moles of reaction arrows. So we'll talk about that in a bit. But if you see this here, you'll see, well, if I talk about my reactions, how many reactions or how many moles of reactions I have per unit, right? They're going to be numerically the same as the absolute value of the change of concentration of A with time. So if A is going down by 1 molar per second, right, and B is also going up by 1 molar per second, right, then I could say I have 1 molar of reaction, or 1 mole of reactions per second, right? So okay, so again, that's a little of a simplification, but I think it'll lend itself in a little while to making the calculations, if not easier, at least make more sense. But be careful. Be careful doing this, okay? Because in that last example, I just had A goes to B, right? But here, look at what has changed. So now we have a stoichiometry change, right? And so what's going to happen here is that it's not always going to be a one-to-one concentration relationship. So in this case, 2 moles of A disappear every time 1 mole of B is formed. And that's straight from the stoichiometry of your balanced chemical equation, okay? All right, so now if I say, okay, so if I want to talk about those reaction arrows, if I want to talk about moles of reaction arrows per unit time, right? Oh, well, so it's like half of, and again, I'm leaving off the negative, I'm being a little loose with that, but it's half the magnitude of the concentration change of A. But it is the same as the magnitude of the concentration change of B, right? So look at what happens to the coefficients here. So so you've got the 2 here, and you've got the 1 here. Well, they become a denominator in finding this overall rate that I'm calling the rate of reaction arrows, right? And so you can generalize this to say the little a and the little b are coefficients here, the little c and the little d are coefficients on the products, right? And so we can generalize that to say that you can use any of those coefficients as a denominator to transform the rate of change of concentration of one of the chemical components here into the rate of reaction. The rate of the reaction here is how that's the thing we're going to use over and over again. And so sometimes I see this one about 50-50. I think sometimes students like to rely on this equation right here and keep this on their cheat sheet and refer to it often to try to transform everything back just using the equation. So you got this rate thing, and you can transform it any way you want to with this, and don't, you're of course not limited to 4 things. You can put anything you want to here, but just know that then if you're using that, your negatives go with your reactants because they're disappearing, and then the rates on the coefficients for the products are positive because they are appearing, right? So so about half the students tend to like to rely on this, and another half tend to like to logic it through, like, well, okay, so if I track my A concentration and it's going down by like 10 molar per second, right? Well, that means I have 5 moles of reactions per second because 10 molar A per second, but there's a 2 there, so that means only 5 reactions, and it also means 5 molar B showing up per second. And I think the stoichiometry can make that make sense, but it works out the same way if you algorithmically crunch it with this equation down here at the bottom. So as an example of what I'm talking about, and maybe this will make the previous slide make more sense. So let's talk about writing a rate expression for a reaction in terms of the disappearance of reactants and the appearance of products, right? So let's say we have this system. Now we have oxygen gas becoming ozone gas. O2 goes to O3. All right, so first step you need to do is you need to balance that chemical reaction. It is not yet, right? So what do we need? Let's see. Well, if we use a 3 coefficient and a 2 coefficient, that'll balance our chemical reaction. All right, that's a step. So we got to get that. Now, given this balanced chemical reaction here, I could go and lean on this equation that we had, right, on the previous slide, right? So because the coefficient is 3, well, I can say it's negative 1/3 negative because this is a reactant. This side positive 1/2 because this guy is a product here, right? So if I ask a question like, so if the rate of disappearance, well, that tells me that must be on the reactant side. If the rate of disappearance of O2, here we are, right? So there's our O2. If the rate of disappearance of O2 is 150 millimolar per second, what is the rate of appearance of O3? And that's over here on the product side. Well, okay, so we know from this that -1/3, right, times, so we have 150 millimolar per second, right, is equal to 1/2 of X here, our ozone. So this is what we wanted to see, right? So there. So we solve for X, right, by dividing both sides by 1/2, or multiplying by 2 if you'd rather do it that way. And so you get okay. So algebraically you get -2/3 of the rate here of 150 millimolar per second. But now I want to focus on that is, here, let me change this to, to highlighter maybe? Yeah, okay, so I want to highlight that this is 150 millimolar disappearance. So think of the dis part of disappearance as your negative, right? So then the negative here, right, would cancel the negative on the 150 being disappearance, right? And so you would get so 2/3 150, so you would get a 100 millimolar appearance of O3. 100 millimolar per second, because the units, no units will cancel out here, so we'll have millimolar per second still. So our rate of appearance is 100 millimolar per second for ozone. All right, now let me look at this the other way that I was talking about, and I can say, well, so wait a minute. All right, so going back to the problem here, I have 150 millimolar per second on this side, right? So this is 150 millimolar per second, right? And so because of this 3, that makes me want to say, well, how many reactions do I have? Well, if there are 150 millimolars per second, and there are 3 moles of reactant every time, so I would say then there are 50, right? You see what I'm doing? I'm dividing by the coefficient there, right? So I've got 50 millimolar reactions per second, right? Okay, cool. And then if there are 50 millimolar reactions per second, and for every one of those reactions I get 2 ozones, then I multiply this 2 by the 50, giving me 100 millimolar per second ozone. So either approach, kind of just number crunching it here by the formula, or logicking it through from the coefficient logic, both end up with the same 100 millimolar per second answer. All right. So in section 12.1, you'll see that I'm pulling this text straight from there just to reiterate some stuff and try to encourage you to read there. That our rate of reaction is talking about the change in the amount that is true. But really, when we're looking at reactions, except for when we're really doing gas phase reactions, for general chemistry, we tend to think in terms of aqueous chemistry, and the reason for that is it's easy to do, it's easy to access in the lab, and it's easy to talk about. So a lot of the times, what we're going to do is we're gonna take it in terms of, just like I did in that last example, of molar concentration units per unit time, right? So the rate of expression is the molar concentration per unit time, and just we could do delta A over delta T is what we're going to try to keep it in, or dA dt would probably be a better way to do it. And so again, this text is straight from your textbook, and I'm not happy with this first statement right now, and I think we can do better than just saying reaction rates are always positive quantities. I think that we would do better here to say that we think in terms of the magnitudes of those rates. But either way, this is the way your textbook puts it, and I just want you to make it make sense that when we're talking about change in concentration over time for your products, then we're trying to say that the concentration of the products is increasing, or in a more generic sense from that last slide, the amount of product is increasing. And when we say that the reaction rate for your reactants is a certain thing, we're going to say that the concentrations of those reactants are decreasing. So I have an ongoing argument about whether we should use this statement the way it is, or whether we should be more generalist and talk about rates as positive and negative. I've not won that argument, but I've also not given it up yet. Usually, at least in Gen Chem, we're usually going to express these changes in molarity, moles per unit time, moles per second, or as I did in that last problem, millimoles. It doesn't matter what power of 10 you put on the front of the moles. You're still talking about concentration in terms of molarity per unit time, per second, per day, whatever. And you can write them in terms of either one. So a thing that you might ask here, and I would love for you to be asking questions like this, is, well, wait, how do you know this? How can you know what is happening over the time course of a reaction? How could you possibly know? Well, so one of the ways we can do that, and one of the things we will do in a lab, is we will take a species in our reaction. It could be a reactant or it could be a product that we can tell something about. So let's say this reaction here, where we take aqueous bromine and we react it with an acid to form products, right? So it turns out that aqueous bromine, we can see it. It turns our solution a brown color, a red-brown color, right? Absorbs at 400, maximum absorption at 400 nanometers, and so we can actually put that in an instrument, a spectrophotometer, and we can actually read the amount of this red-brown light that is absorbed here. And we can see how much there is. We can set up a standards curve and actually graph how much there is, and so we can watch it over time as the brown color fades out. And so we can say, oh, well, look, the brown color is coming from this bromine dissolved in the water, and the brown color is going away over time. And so we can see the concentration of the bromine going down over time. So we'll shine a light through there, and we'll actually use a detector to quantitate the amount, and we'll use it to calculate a change in the change that we'll see, the change in absorption, and then we'll calculate from that a proportional change in concentration of something. And so we'll see. Now, this don't be confused by this graph. This is showing three different snapshots, right? And so this first one, T1, is over here, right? When we got this deeper color, and so we got a high absorption, right? So we might say, oh, look, it's absorbing a lot of stuff. There must be a lot of this component there that's dissolving, that is absorbing that light, right? And then time 2 here is the middle hump, and it says, well, it's still high, but it's not as high as it used to be. And then time 3, and we of course would be timing this with a clock, and we would say, well, now it's pretty low, and eventually it'll go away. So, or it might, depending on what your next unit are, what our equilibrium concentrations are. But you can just see that over time, the concentrations are going down. And so you probably know me by now, and what I would likely do is I would set up my Excel, and I would plot this thing over time, right? So here are my time units, right? So I've got different time stamps here. This happens to be in every 50 seconds. It wouldn't have to be, but you plot it over time, and then you would take a reading using your spectrophotometer, and then you would convert that to a concentration of bromine. You would say, okay, well, we started out, and here's our 0.0120 molar bromine, and then we let the reaction happen, and over time we saw the concentration come down more, and so we get this curve of, over here we have a concentration axis, it's in molar here, and here we have a time axis, and so you have this concentration versus time space. And so the idea, we could find an average rate. We could find from any point to another point, we can find the average rate with just the delta concentration divided by delta t, right? Which is your same as your delta y over delta x, right? So like slope is if this were linear. And so we can find an average rate there from any concentration from a final to an initial, and a time differential there. Or, if you know about calculus here, this is where you get into the limit of x plus delta x, where delta x approaches 0. So what you're doing is you're saying if you can get close enough, you can find the slope at one point on the line. But now here's the thing. If you looked at the slope right here, that is a steeper slope. It's negative, but it's still steeper, higher magnitude, than the slope is here in the middle. And then that in the middle is in turn steeper than the slope is here. So our actual rate of reaction is slowing down over time. And so make sure you take a read in your textbook for this section here, because my take on this, especially on the first one, is slightly different than the way your textbook puts it. So I'm interested to hear your discussion of what I'm saying here about my phase of reactants versus how your book puts it. But what we're talking about is different factors that can affect the rate, the kinetics of any given reaction. So you can do some things. You could, number 2 here, you could change the temperature of a reaction, and keeping it simple, just think in terms of heating a reaction up to speed it up. Now, it's not perfect that it's always increase in temperature increases kinetics, but I think that's the simple interpretation of it, that's the easiest way to look at it. But another thing that happens is usually, again, not always, but usually, you can increase the rate of a reaction by increasing the concentration of the reactants. So it'll react faster if it's more concentrated, and so you can change your rate there. Now I would add to number 3 that the concentration of reactants, yes, but also the concentration of products, and this would invert it. Usually, as your products increase in concentration, your reaction rates tends to slow down. So we can talk about that too. But again, that'll be easier to talk about once we have equilibrium to go with it. Now I'm going to jump back up to number 1 and think about it. So talk to me about this when we get to class and about how I put it differently. I'm going to say the phase of your reactants, and what I think what causes me to look at this is my environmental geology background, and I want to think, well, now look, the state, your book says the state of the reactants, but I think it matters more. I'm using phase differently than state here because I care whether it is a liquid versus an aqueous versus a solid versus a absorbed versus an adsorbed state. I think all these different phases, even though they might overlap some of the states, there's more difference than just states involved. And another thing that I think that they leave off that's very, very important is the surface area function. So in general, the more surface area of a solid that you have for reaction, the faster your reaction rate. So if you take a block of aluminum and you expose it to a torch, to like a propane torch, it's unlikely that anything bad will happen. But if you were to, please do not do this. If you were to finely grind that aluminum into like a super duper super fine powder and expose that to a propane torch, well, you probably just exploded yourself because of changing the available surface area. You make that a much faster reaction from aluminum to aluminum oxide, and it's very exothermic and dramatic, and you really don't want to be anywhere near it when it happens. And you might think of it as rocket fuel, because that's kind of what it is, solid rocket fuel. So you don't want to be in the presence of rocket fuel finely divided aluminum when it does that. Now, number 4 down here is the presence of a catalyst. So what a catalyst does is it speeds up a reaction, often by controlling the orientation of different reactants, or otherwise changing some of the function of how fast it can go. An important piece of catalyst thinking is that the catalyst does not change the overall thermodynamic stability in such that it doesn't change whether or not a reaction is thermodynamically stable, thermodynamically favored, anything like that. It only determines how fast that reaction will go. So thinking back to our graph of the state variable earlier, right? So let me throw that up there, right? So we had that exothermic system here, right? So, and then we had this delta here, this E sub A for energy of activation, right? So what I'm saying here is, in the case of a catalyst, it doesn't change this overall thermodynamics, but it might well give it a much lower hill to get over, in which case increasing the kinetics of the system without changing the overall thermodynamics. Okay, and now please do watch my graphics up here for my joke. Let me know if you got it. But y'all know already how chemists love to try to linearize things. Okay, so we like to try to see if we can hammer on our data some way mathematically in order to try to get it to turn into a straight line. And once we can get it into a linear function, then we can, we think we know something about it, right? So in this case, the way we do that is by integrating and rearranging, okay? And so if we have zero order such that, what I mean by zero order rate law here is that the derivative of the concentration with respect to time, or I could have put delta A, delta T here, is equal to a constant. So the amount that this reaction is running is a constant rate. Now, if I look over here on the right side of this, note that this constant is not multiplied by anything. And if I were to put here, if I were to say equals K times concentration of A, right, to some power, well, for it to be equal to this piece here, the only power option I have here is a 0. And if if my concentration is raised to a 0, then you don't care what the concentration is, because unless it's 0, any number raised to a 0 power is just 1. Okay, well in that case, then if it's any concentration raised to 0 is 1, then it's this constant, this k value here, right, multiplied by 1, right? So it's basically it's just k, right? So our rate is a constant regardless of what the concentration is. And so now if you take that and you, well, okay, so for my math people, for folks that do like the calculus, so I will take this this PowerPoint and I will upload it to our website. And you can go into this PowerPoint here, and where I've got this screen, and it says that magic was done by the derivative. Maybe I should call them integral fairies. I don't know, but we're going to integrate behind the screen here. Okay, so if you want to see the integration process, it really is here behind the screen. Just go into the PowerPoint and move the blue box off to the side, and there's your integration underneath it. But if you don't want to do the calculus right now, then you can just take this other route of believing me. And if we have this derivative right here, this derivative is equal to k, right? I can integrate that and say, oh, well, okay, so for concentration at time t, any concentration at time t, minus our initial concentration is equal to negative, that constant, so that's saying k, times the time. So I can take whatever our constant is, multiply it by how long the reaction's been running, and it tells me the difference in final and starting concentration, right? I can rearrange my terms now, and now I have a function with respect to t, function of time here, is equal to negative kt plus an initial concentration, which is y equals mx plus b. So now I have this linear function. I can plot it in Excel, and I can get slopes, and I can do all these different things. It is nice and linear. So we take a 0 order rate, integrate it to a linear concentration versus time function. Okay, but that's only 0 order. So now first order. So for first order, we have a situation where the rate of the reaction does depend on the concentration. So when we have a higher concentration, we get a faster reaction. So if you look here, right, like at first, if you have a really high concentration, it drops quickly. But then as it drops quickly, that means the concentration is going down, which makes it react less fast and less fast and less fast. And so eventually you're getting a very, very slow reaction because your overall concentration is low. And that says that our rate is dependent on our overall concentration, or you could say your derivative is dependent on your concentration, right? And so if you take this and again do the integrals here, you get this situation right here that now, as opposed to that previous 0 order, now we get a situation where concentration at some time t divided by the initial concentration is equal to the Euler number raised to the negative kt. So here's my k. It's the same k that we had up here, and t is my function time, right? So now here's our system, and to linearize it, what I'm going to have to do is I'm going to multiply on both sides by my initial concentration, right? There we go, right? And then I'm going to have to do the logarithms. So I'm going to have to take a natural log of this side, right? And then when I do a natural log of this side, and MathLab, our math tutoring center, will be happy to help you figure out how this natural log situation works here. But the basic idea is you've got this term, your initial concentration, multiplied by this exponential term, right? And so laws of logarithms say that you can split those by a plus now because they were multiplied here, and you're taking a natural log. So now they're an addition of terms, and so the natural log is going to get rid of the e function, right? And so you're going to have a negative kt. So that piece becomes the negative kt. But then the natural log of this initial concentration here, you've still got natural log initial concentration. And now you took a natural log of this side, you have to take a natural log of this side also, so you have ln of concentration at time t is equal to negative kt plus ln initial. Oh, but look at that, look at that. If you were to plot this on your y-axis, right? Look at that, plot that on your y-axis, and then you could call negative k your m, that's your slope. So you got y equals mx plus, and then this initial concentration can be your b. So basically we have linearized the integral of this situation. And for the purposes of this course, we'll only go as far as the zero order, first order, or second order when we're talking about these integrals. But you can see that, well, in this case, not only does the derivative depend on concentration, it depends on the square of the concentration. So this is a case where it really, really matters how concentrated. And so this slope drops really drastically, and then it levels out really drastically also. And then if you take the integral here behind the screen, you end up with this situation right here. 1 over concentration time t is equal to 1 over initial concentration, and that is equal to the k times t. And you linearize this one here by taking 1 over. So the inverse of the concentration time t is equal to kt times the plus the inverse of the initial concentration. And so again, you have a y here, this side equals m is the k, and then t plus the b here, the intercept is going to be 1 over initial concentration. Well, there we are with another of my intended 15-minute videos, which I'm looking at the top of the screen here, and it says 56 minutes. I never get these things under 15 minutes. I don't know why. I think I might. But anyway, so from here, for the next one, make sure then to read everything now in Chapter 12, so that all these things come together. So read anything left in Chapter 12, and we'll make another video for lecture video 8 next, and I'll see y'all in class.